Hi, in the previous video, we looked at the relationship between the voltage and the current of a capacitor, and we found the relations, and I have put the relations here on the slide. What I want to do in this video is look at the output of a capacitor for a very specific kind of a signal, okay? And I want to take a look at the output of the capacitor for a voltage which is given by, let's say, A sine omega t. What will be the current in response to this voltage? Okay, the current is going to become what? It's going to be C and then the differential of the voltage, and the voltage is given by sine omega t. All right, so that is going to turn out to be C. Well, I need to write out amplitude A here. So C times A, and then it is omega cos omega t, which is the differentiation of sine omega t, right? Uh, now, from this equation, what we can try to do is we can try to derive something analogous to what we had in resistors, which was the ratio of the voltage and the current, right? In a resistor, what's the voltage V? What's the voltage V over I called? It is called the resistance, right? Similarly, what we want to do is we want to find out the voltage divided by the current for a capacitor, and in case of a capacitor, we let's call it x, and let's call this x is called the reactance of the capacitor. Okay, so we want to calculate this reactance, but as we know, we really cannot get this equation in general. So what we are going to do is we are going to say, well, give me the V over I for a specific frequency that we are using. Okay, so we want to get V over I for when, let's say, the voltage is a sinusoid of a specific frequency. And so that's where we are going. So let's try to do that. Now, this current can be written as C A omega sine omega t plus pi over 2, where pi by 2 is 90 degrees, right? So now you have a sine wave in your current and a sine wave in your voltage. But the issue is that there is a phase difference. And therefore, if you divide the voltage with the current, you're not really going to get a uh, get a value which is easy, which does not have this time dependence. So here's what we are going to do then. What we'll do is we'll take a look at the magnitude of the voltage. And what's the magnitude of the voltage? It's A, right? And what's the magnitude of the current? It's equal to CA omega, or we could write it as omega C times A. Okay. And once we have the magnitude, you could talk about the magnitude of the reactance. See, V over I, which is here, V over I we defined as X, which is the reactance, right? So let's get the magnitude of the reactance. And what does the magnitude of the reactance turn out to be? It is basically mod V over mod I. And that is equal to, what's that going to turn out to be? 1 over omega C, right? And now let's try to figure out what's the angle of the reactance. So let me just clear up the screen a little bit so that we are able to write the equations for the angle. So what I'm wanting to do is trying to find out the angle for x, and or the phase of x, and x is what? X is V over I, right? And do you remember what the how do you find the angle? If you remember complex numbers, what you do is this is equal to angle of V minus angle of I, right? And what's the angle of V here? It's 0, the phase of, and the angle of I is pi by 2. So what we get here is minus pi over 2. So what that tells us is x is not a real number, right? X has an angle and a magnitude. It's not a real number, it's a complex number. Okay, and if you convert this x into a rectangular format, what you would get is x equal to 1 over j omega c. Okay, but j is the square root of -1, it's the complex number. So that kind of helps you to see how a capacitor behaves. So when omega is very small, let's say it's zero, then what is the value of x? It becomes infinite. And if x becomes infinite, what is the current flowing through a capacitor? It's zero, right? Because the voltage is not changing, the current is zero. And that's exactly what this equation also tells us. Okay, now if omega is very very large, so let's say it's infinite, then what happens to x? What happens to x is it becomes zero. Omega is infinite, so x becomes equal to zero. And what is the current that will flow through the capacitor then? An infinite current. So if you plot then, if you plot a frequency, on the x-axis you put frequency, and on the y-axis you put x, and let's say you put mod x. So what kind of a curve would you get? So mod x is going to be infinite at x equal to 0, and it's going to be 0 at omega equal to infinity. And it's got a 1 over omega dependence, right? So it's going to be like this. So the capacitor basically is a frequency dependent resistor, you can call it, right? It makes some changes in the phase of the signal as well, but if you just look at the magnitude, you can call it a frequency dependent resistor. So as the frequency of the input or the voltage increases, the impedance of your capacitor or the resistance offered by the capacitor to the flow of current actually reduces.